Hello! In the previous video we talked about the Brayton cycle and we stopped at the example of a Brayton cycle with a reheat combustor. So 1 to 2 will be the isentropic compression from the compressor. Okay, 2 to 3 is the isobaric heat addition. Now 3 to 4 is the isentropic expansion. And 4 to 5 will be the isobaric compression. And 5 to 6 is going to be the isentropic expansion. And obviously point 1 and point 6 are on the same pressure. So we see that by adding this second combustor, the work we get, I'll mark it with green on the graph, is a lot bigger for this cycle. We also increase the efficiency, which is this useful work, divided by the heat we offer under this graph. Now let's look at another interesting setup in the Brayton cycle. So let's say we have compressor 1 to 2. And instead of continuing the compression, we decide to take the air out and pass it through a heat exchanger, from which we will reject all the heat that was generated from the compression, and then we'll take the air and pass it on a second compressor to here, point 3, and we're going to take the air at point 4 over here. So let's look at this process now on the PV diagram, pressure specific volume. So we start from point 1, and normally we would compress under constant entropy and follow this line, and I write here S equal constant. Okay, so normally we would compress on the isentropic. Now what we do is we compress from 1 to point 2. Then we keep the same pressure on the heat exchanger and we move at a lower temperature. And then we compress again isentropically, S equal constant again, to point 4. So now the work that we need to pay to the compressor is the area under here. So by adding this heat exchanger, where we call it intercooler, we save this work over here that we would have to pay if we were compressing from point 1 to point 4 prime. So let's look at this process on the TS diagram. We start from point 1, we compress isentropically to point 2. This is our P1 line. Point 2 is at a pressure P2, on which we move on this pressure to come to point 3 over here. Then we compress again to point 4, which will be on the isobaric line P4. And if we had only one stage compressor without the intercooler, would go from 1 to 0.2 to all the way isentropically straight up to 0.4 prime. So the area under the TS diagram is heat. So this blue area here is the heat that our intercooler rejects, and that's why we move from T2, higher T2, to lower T3 over here. Now let's have a look at this regenerative gas turbine with reheat and intercooling. So in this example, we are not going to consider our compression and expansion isentropic, but instead we're going to use the isentropic efficiency. So we start from point 1. On the TS diagram, we would normally go vertically up to 2s, but instead we create entropy or go to point 2. We'll continue on the isobaric line from point 2 to point 3, rejecting heat, so going to lower temperature. We're going to compress from 3 to 4 instead 4s, which is the isentropic. Up to 0.5, we're adding heat from the regenerator. 5 to 6, the heat is offered from the first combustion chamber. 6 to 7s is the isentropic that we're not going to follow. We're going to follow the isentropic efficiency. We'll go to 0.7. 7 to 8, again at constant heat, at constant pressure, we add heat. We go to higher temperature, 8. Instead of going to 9s isentropically, we go to 0.9. And obviously 0.9 is on the same isobaric line as 0.1, but 0.10 is the exit from the regenerator, which is at a lower temperature than 0.9, so somewhere here on the TS diagram. Now let's calculate the total turbine work. So we have the work turbine divided by the mass flow rate, okay, will equal H6 minus H7, and we add for the second turbine H8 minus H9. But because we have the isentropic efficiencies of the turbine, so we have NT1 and NT2, okay, we can write this as NT1 multiplied by H6 minus H7s plus the isentropic efficiency of turbine 2 times H8 minus H9s. So in exactly the same way, we can find the total compressor work, WC dot over M dot, which will be the work for compressor 1, H2 minus H1, plus the work we need to offer to compressor 2, H4 minus H3. We have the isentropic efficiencies for compressors 1 and compressor 2, so we can write this as H2s minus H1 divided by N compressor 1 plus H4s minus H3 over N compressor 2. We can find the total heat added as Q dot total over M dot. It will be H6 minus H5 for the first combustor, and H8 minus H7 for the second. H8 minus H7. Now the efficiency, we know how to find it, dividing the net work by the total heat. It's more interesting now to define the regenerator effectiveness and regenerator, which is the energy we actually get, so H5 minus H4 divided by the maximum energy that we could potentially get, which will be H9 minus H4.